Hey guys, this is your final section from chapter 14. So we're going to go ahead and go through this pretty quickly. Um, so these are your essential questions for section 3. The last thing that we have to talk about in this chapter is behavior of gases. So we're going to talk about how gases actually exert pressure on their containers and how they're affected when pressure, temperature, or volume are changed. So the first law concerning gases is Boyle's law, and it has to do with volume and pressure. And so the first thing that we have to remember before we talk about this stuff is that from section 1, we saw that a gas completely fills its container. Those particles are very spread apart, they're moving very quickly, and they're going to take up all of the container that they're in. So we're going to use a balloon as a reference a lot of times because we've all played with balloons before. So balloons remain inflated because of collisions that those gas particles have with the walls of their container. So in other words, as those particles are inside that balloon, not only are they spread out and moving quickly, but every single time one of those gas particles hits the side of the balloon, that's what causes that pressure that you feel on the outside of their balloon. That's how they stay inflated. So you can see on my little illustration up here in the corner that those gas particles are spread out, moving quickly, and then it shows that movement running into the outsides of the container, and those orange arrows are that pressure that it puts on the outside of the balloon, which is why they stay basically taut on the outside instead of all of the gas particles just kind of sitting at the bottom. In that case, the balloon would kind of shrink down. So, like I've been saying, those collisions with the side of the balloon are what actually causes the gas inside of it to exert pressure on the container that you can feel on the outside. So, what is the relationship between volume and pressure? So, if we think about it this way, if we were to decrease the size of the container, so use a smaller balloon, would the number of times the particles hit the walls of the container increase or decrease? So if I put the same amount of gas particles in a small balloon versus a big balloon, in which balloon would the particles hit the sides of the container more often? And it becomes pretty clear, if I put the same amount of gas in two places, but one of those places is smaller, they're clearly going to run into the sides of that smaller container way more often. So Boyle's law says that if you decrease the volume, in other words, you make the area that you put the gas smaller, if you decrease the volume, so you make it smaller, and then the temperature stays the same, then the pressure of the gas will increase, and that is because the particles run into the sides more often. So those sides of the container are closer to the particles run into the sides more often, and so you have greater pressure. So it's kind of like when you have your balloon and then you start squeezing the outside, you are making the volume smaller. And as you start squeezing the outside of that balloon, you can feel that pressure against your hands getting greater and greater. And so this is just a little visual that I have found to kind of help you understand that. You can see as it proceeds from left to right that the volume of our container got smaller. We went from this huge area to this very small one. And you can see that the particles were able to spread out a lot more in this big container. But when we got to this small container, all those particles are closer together, and so they have no choice but to run into the sides. And so the reverse is true as well. An increase in volume, so going from this size up to this one, is going to cause the pressure to drop because the particles don't run into the sides as often. And there is an equation for Boyle's law. P1V1 equals P2V2. In other words, if we know the pressure and volume of one container and we want the volume of the next container to be a certain number, we can figure out the pressure that we need in order to achieve that. So initial pressure times initial volume equals final pressure times final volume. I've included an example problem, but I'm not so much worried about the math while you guys are working at home. If we were all together, we would work on it together, but since I can't help you as much as I'm used to, I'm going to provide this example problem, and I want you to go ahead and try it. but I'm not worried so much about the math aspect. I just want you to understand the relationship between pressure and volume. So as volume goes up, pressure goes down. So you can imagine those opposite arrows that I draw on the board all the time. And then we talked about direct and inverse relationships. We talked about those a lot as we went through prior chapters. And anytime we had one arrow going up while one arrow was going down, it's called an inverse relationship. So pressure and volume, according to Boyle's law, have an inverse relationship. The second law concerning gases is Charles' law, and it has to do with temperature and volume. And so, using what we know, we can imagine what happens to a gas as it is heated, because we talked about temperature in our last unit, and the difference between a gas at a cooler temperature and a gas at a higher temperature is what? Speed of the particles. Yes, that's right. I know you were thinking that. So, a gas that is heated is going to have greater speed in its particles. And so they spread further apart, they're moving faster, they run into the sides more often. And so Charles realized this, and he says, well, the volume of a gas has to increase with increasing temperature, because if you heat up those particles and they're moving faster, they have to spread farther apart. And if something spreads farther apart, that means that the volume or amount of space it takes up has to be bigger. And that's exactly how a hot air balloon works. That flame heats up the gas particles inside the balloon, speeding them up, gets them spread further apart. And so the balloon, the air inside the balloon becomes less dense than the air outside the balloon. And so we go back to Archimedes. So it all relates to all the things that we've talked about the whole chapter. So the reverse is also true. If the volume of a gas decreases, that means that the temperature has gone down. So again, we can do some calculations with Charles' law because he went ahead and put it into math. And so kinetic theory has to do with this as well, because we were talking about temperature and we talked about how the particles get faster, move farther apart. So you can see that in my illustration. And so here's that mathematical equation that he came up with when he realized this relationship, which is a direct relationship, because when temperature goes up, particles spread further apart, which means volume goes up. So my arrows would be in the same direction, which means direct relationship. But the equation that Charles came up with in order to relate these two variables was initial volume divided by initial temperature equals your final volume divided by final temperature. And so again, I did put an example problem on here, and I hope that you will try it on your own. And but again, I'm more concerned with you knowing the relationship between these variables than getting the correct answer on this example problem. But I will post the answers to them later on. So you will get to see if you got them right if you decide to try them, which I hope you do. So that ends this chapter. The next thing that I'm going to post next week is going to be some practice that includes the entire unit. And then we'll be moving on to something new. So I hope you guys are still following along and trying to learn a little bit of something. And I'm going to try to post some at least virtual labs for you to do, if not some real labs that you can do with some things you have at home. So stick with me a little while longer. It'll give you something to do, and I will talk to you soon.